Good evening, students. Am I audible? Vijay Lakshmi, Jitendra.
Yes, sir, audible.
Okay, thank you. So, on behalf of IGNOR Regional System Bhubaneswar, welcome you all to this online platform, which is based on your conduction of your online class of diploma in agricultural history program of your MCH-2 score or paper. And today is the last day of our discussion of different separation techniques. And from the beginning, we have discussed the physical separation methods. It includes your filtration, distillation, fractional distillation, etc., followed by the solvent extraction part 1 and part 2. Then on the day 2, we have discussed the planar chromatography and the basic of chromatography. On the basic of chromatography, we have learned that different stationary and liquid phases are there, which are based on different physical and chemical mechanisms, on the basis of which different chromatographies are classified. So the planar chromatography, it is made of two types, two-dimensional, three-dimensional. In the two-dimensional planar chromatography, we have vapor chromatography and linear chromatography. And the three-dimensional chromatography is a color chromatography. So in vapor chromatography, it is again of two types: ascending vapor chromatography, descending vapor chromatography, in which vapor it acts as the stationary phase and is a suitable solvent for the element which is acts as the mobile phase. Similarly, in your thin layer chromatography, the thin layer is uh, your a thin layer is made by using slurry of silica gel or alumina, and accordingly,
सर स्क्रीन अवेलेबल नहीं शो हो रही आपकी।
hello.
स्क्रीन शो नहीं हो रही।
हाँ, मैंने स्क्रीन से अभी तक नहीं किया, मैं प्रीवियस क्लास का बात बता रहा हूँ, ठीक है। अभी मैं थोड़ा याद दिला दूँ क्या क्या हम लोगों ने पढ़ाई किया है, उसके बाद मैं स्क्रीन शेयर करके आपको पूछूंगा कि प्रिंसिपल। सो in your column chromatography, you have a column which is packed with some cotton below and above, and within or in the mid, we have the silica gel of different base sizes, and followed by we have discussed the liquid chromatography, which is maybe LSC or LNC, liquid solid chromatography, liquid chromatography. In LSC, the mechanism is adsorption, whereas LNC, we have the mechanism of partition. Similarly, we have the gas chromatography. It will be GSC or GLC. If it is GSC, gas solid chromatography, then the stationary phase is a solid. If it is GLC, the stationary phase is a liquid. And accordingly, the partition mechanism or adsorption mechanism is applied on the basis of the stationary phase. And in GSC, the gas phase is always treated as the mobile phase. And yesterday we have discussed the ion exchange chromatography and size exclusion chromatography. So in ion exchange chromatography, we have different ion exchangers, the cation exchanger and anion exchanger. The cation exchanger is made up of negative ions and the anion exchanger is made up of positive ions. And also these ion exchange chromatography, these are mainly used in your demineralized water plants in large scale industries. Similarly, the side exclusion chromatography is also known as the gel filtration chromatography or gel permeation chromatography. In both the cases, the column is now filled with some beads with some pore sizes, and the sample containing different size particles uh, are now adjusted with that holes or pores. The large size particles are filtered, or it can be extracted or separated first, followed by the small size particles. So after this we have covered, and today we will have the your 2 units, the last 2 units. The first one is just what I am sharing this screen with you. I think now it is shared. Uh, so is it visible, Jitendra?
Yes, sir. Visible.
Okay, thank you. So this is the unit 11 we have, that is a membrane separation, which is in this part we have the osmosis. The main aim of discussion will be osmosis. And to discuss this unit, I have a I have a small presentation for you. There is a membrane process or membrane separation, in which we will discuss the reverse osmosis, ultrafiltration, and microfiltration. So ultra means 10 to the power minus 6, micro means 10 to the power minus 3. So let's have the membrane separation process. So as the name of this process, it is also well explained that for the separation of particles from a solution, a membrane is used. Like whenever we filter the tea which is prepared in our home, a small cotton or a maize with different pore sizes are used, and that is also used as a membrane for the separation of particles of tea from the tea solution. Similarly, we have the membrane process. So the membrane is of many types. For example, if the first one is your membrane. So membranes are thin films of synthetic organic or inorganic ceramic materials which can bring about very selective separation between a fluid and its component. The fluid may be a gas or a liquid, but in environmental engineering we are more concerned with water and wastewater. So this is just a basic definition of a membrane. Shows that membranes are thin film of both synthetic, organic, or inorganic materials, which are very much used for the separation of different particles or residues from its solution. So this is the microfiltration we have. So under this filtration, we have a dead end filtration in filter cake and membrane. So this is acts as a separator or a membrane we have, above which it is known as the filter cake. And when the solution is now placed inside this part, then gradually with within these small pores, the different particles gets passed through that maze or membrane. So just see here, this is the membrane we have. This is cross flow microfiltration, where we have a membrane here, and the solution or we will say the sample, it is flow through the horizontal direction. Then what happened? As this is a mass is there or a membrane is there, then the different particles gets filtered on the basis of their sizes. They are passed through this small pores. So here the retentant, this one, the retentant may be recirculated to the field. So it will be recirculated. A dynamic membrane may be created by adding lime or potassium permanganate to the feed to precipitate manganese oxide on membrane. So membrane operation, if 100% in the suspended solid is passed through this horizontal direction, then 50% may be remained as the colloid and 50% may be passed through the membrane as the permeate. So this is the membrane we have. The application of membrane in wastewater treatment. So this may be used as the pressure-driven solid liquid separation process, tertiary treatment of wastewaters following following secondary sedimentation, production of high quality effluent in a reuse scheme, and also we have alternate to sedimentation tanks for solid liquid separation and aerobic biological treatment and anaerobic biological. So we have different applications of this membrane separation or microfiltration, under which we have aerobic biological treatment and anaerobic, that is in presence of oxygen or air, and in absence of oxygen and air we have the sedimentation tanks are there for solid and liquid separation. In the aerobic biological treatment where the oxygen is very plenty available. So here what happened? We have the pre-treatment of the sample of the air, then your sedimentation tank, the sample is now moved to the sediment tank, which is again passed through that aerobic biological process. So the sediment tank may be treated as the primary sludge, and your microfiltration it is treated as the secondary sludge. Then after that, your final effluents are separated. That is your biological oxygen demand and suspended solid. Okay, so this is how your separation made. Then we have the membrane anaerobic reactor. So this is a reactor we have where ultrafiltration or microfiltration units are there, and accordingly the flow of the influent will be in this direction. That is my anaerobic reactor. Two, we have the separation units here, and after separation the effluents are separated, and the the influent which is remain inside the ultrafiltration or microfiltration chamber, they are again recycled back to this energy. So advantages of membrane processes, they are usually continuous, comparatively low energy utilization, no phase change of contaminants, small temperature change, modular design, minimum of moving parts, physical separation of contaminants. So these are some advantages of our membrane separation. So this process is very much continuous process. So comparatively low energy utilization is required. No phase change of contaminants are there. Small temperature change is made. Modular design is there. Minimum of moving parts is there, and physical separation of contaminants is there. And the filtration range, so what is the range we have in micron scale? We have from 0 to 0.001 micron of particle. This can be separated using reverse osmosis or RO, and from 0.001 to 0.01 it is nanofiltration, factor minus 9. So from 0.01 to 0.1 we may have the ultrafiltration 10⁻⁶ to 10⁻³ that is the microfiltration. So the RO it may be applicable to ionic range. For nano it is micromolecular or macromolecular range, and for microfiltration or somehow it is ultrafiltration, we have the microorganism separation or coarse particles are there. So this is how your, and this is the molecular weight, MW, molecular weight of the compound. So these are some applied pressures which are applicable to different separation techniques based on membrane separation. So in reverse osmosis we have the 100 to 800 psi, that is equal to 1000 to 5500 kPa, that is kilopascal. The ultrafiltration of 5 to 100 psi, and microfiltration is very low pressure. So microfiltration begin consideration, these are very high flux. Then we have the back flushable, high membrane area to volume ratio, allowing low pressure drop while maintaining high tangential velocities, simple installation and continuous operation with minimum supervision, low operating pressure, easy maintenance and simple membrane replacement, low energy consumption, relatively low capital cost. So these are some consideration of our microfiltration. It has high flux, back possible, high membrane area to volume ratio, simple installation and continuous operation, low operating pressure, easy maintenance and simple membrane replacement, low energy consumption and relatively low capital cost. So microfiltration current applications. So these are used in wine industry, dextrose classification, eggs removal from gelatin, beer classification, pharmaceutical or biological application, and municipal waste treatment. So this is the application of your microfiltration in current scenario. So in future we may use this microfiltration to drinking water, or hydrocarbon separation, milk to fat separation, food and beverage, industrial wastewater, paint, biotechnology. So these are some areas in which the future the microfiltration process or application may be applied. So similarly, we have the ultrafiltration application. So in current scenario, we have the juice clarification, increased cheese yield, gelatin concentration, electroplating wastewater, protein from cheese, concentration of oil emulsions, pharmaceutical industry, grey water, industrial wastewater. So in future, we have the domestic wastewater, more industrial wastewaters, protein harvesting, petroleum processing, wastewater reuse, potable water, and that is blood recovery, abattoir, pulp and paper industry, and many more. So these are some applications for micro and ultra filtration. Then the very well known the popular concept, that is reverse osmosis or RO. So this is a different process of your micro filtration or ultra filtration, because so first from that is osmosis, then we will move to reverse osmosis. So osmosis is one, that is the separation of solvent particles from a low concentration solution to high concentration of solution through a semi-permeable membrane. So what is a semi-permeable membrane? The semi-permeable membrane only allows the solvent particles to pass through it. It is known as semi-permeable membrane. So if you experience a small thin coating of a boiled egg, if you are if you just detach the outer layer of a boiled egg, and you just experience one small thin layer is there with a very fine like a it's like a fine thin layer, very thin layer is there, which is which may be called as a semi-permeable membrane, which allows the solvent particle only the water. We may say it is the universal solvent is water, so it allows only the water particle pass through it, leaving the all the impurity or the residual particle uh, back in the solution. So that means semi-permeable membrane is a special type of membrane which allows only the solvent particle to pass through. So whenever there is movement of solvent particles from a low concentration to higher concentration concentrated solution through a semi-permeable membrane, it is called osmosis. So what is reverse osmosis? It is reverse of osmosis. That means it is the movement of solvent particle from higher concentration to lower concentration. That means it is the reverse of that osmosis. So it is the movement of solvent particles from higher concentration to lower concentration through a semi-permeable membrane. So semi-permeable membrane is very important or one of the vital aspect of a reverse osmosis process. And this reverse osmosis, or in short it is RO, is used, or this mechanism is used in all the water purifiers that are used in our homes or in various places like Aquaguard, Kent. We have the Deep Pure, the different your water purifier companies are there. So they are using the semi-thermal membrane to separate the dissolved solid present in water, and we will get a, mineral water, a demineralized water. When we say that these mineral waters are devoid of the dissolved solid present in the water. So only the solvent particle is allowed to pass through this membrane, and in reverse osmosis, the movement of solvent particle is from higher concentration to lower concentration. So in osmosis, it is the reverse, lower concentration to higher concentration. In reverse osmosis, it is higher to lower. So very different process. It is a solubilization diffusion technique that makes the semiconductor membrane, which in turn acts as a barrier to dissolve salts and inorganic molecules. It also confines organic with molecular weight greater than 100. Reverse osmosis membranes do not have identifiable pores as in microfiltration or ultrafiltration. Filtration to small atomic size. So these are some characteristics of RO. So application of RO, just here see, we have the desalination for potable water, from C, from brackish water for effluent reuse, ultra pure water from semiconductor, ultra pure water from pharmaceuticals, ultra pure water for medical use. Then we have the boiled feed water, boiler feed water, and treatment of hazardous material. In future, we have the chemical process industries, metals recovery, food processing, uh, WWT, textile water waste, reuse, that is water waste treatment, pulp and paper water waste treatment, contaminated land remediation, industry, dairy industry of wastewater. So in all these areas, the RO is used, and just remember, the RO, it is a very important scientific mechanism of separation of dissolved solid from your solution. Then what happened here due to presence of your semi-permeable membrane, the dissolved solids get separated, or we may say it is the movement of solvent particles from higher concentration to lower concentration. So that's why this is a very important phenomenon. And also the pressure required at the lower concentration part of the solution to stop osmosis, it is called osmotic pressure. So osmotic pressure pi equal to CRT, where C is the concentration of the solution, R is the universal gas constant, and T is the temperature. So this is the basic difference between ultrafiltration, reverse osmosis, and microfiltration. So ultrafiltration, it operates on liquid colloidal water. Osmosis required extensive treatment of colloids. Microfiltration rapidly cooled by colloids giving high replacement cost. In ultrafiltration, we have low pressure, that is 2 to 6 bar. In high pressure, 10 to 30 bar, and low pressure, 2 to 4 bar. Low energy consumption, high energy, and low energy. This is high recovery up to 95%, low recovery under reverse osmosis. So we have the recovery percentage of 50 to 80%, and the microfiltration we have generally the 100% recovery. Then we have the next part, that is the chemical tolerance, that is the pH. So the pH for our ultrafiltration, it is 1 to 13 range, and under reverse osmosis it is pH 2 to 11, and for your microfiltration it is maybe 1 to 10. So high temperature up to 80 degree is permissible for ultrafiltration. So maximum 45 degree centigrade is permissible for RO, and high temperature is possible for microfiltration. Then we have the high resistance to oxidation or oxidizing agent, limited resistance to oxidizing agent, and high resistance to oxidizing agent. Then the stream sterilizable, stream sterilization not possible. It is available, it is not possible. It is also possible. Hygienic module designs available, modules not as hygienic, hygienic design available. So this is the basic difference between the the three membrane separation process we have. That is ultrafiltration, reverse osmosis, and microfiltration. Then some property of typical commercial ultrafiltration membranes. The ultrafiltration membrane may be made up of polysulfone, where the pH is 2 to 12, the pH tolerance limit. We have the pressure of 15 bar, and maximum temperature that can be made will be 70 degrees centigrade. This is mistakenly here it is not bar, degree centigrade. Polyacrylonitrile 2 to 10 pH, 10 bar and 60 degree. Cellulose acetate 3 to 6 pH, 25 bar atmosphere and 30 degrees centigrade. We have polyether sulfone 2 to 12 pH, 30 bar pressure and 70 atmospheric pressure, temperature 70 degrees centigrade. Fluoropolymer 2 to 12 pH, 10 bar pressure and 60 degrees centigrade maximum. Polyvinylidene chloride 2 to 12 pH range, 10 bar pressure and 70 degrees centigrade at temperature. Polyvinyl chloride 2 to 12 pH range, 10 bar maximum pressure and 50 is the maximum temperature. So this is all about uh, your membrane separation. So let's have the PDF. We have the reverse osmosis, nanofiltration that came from -9, ultrafiltration that came from -6, and microfiltration came from -3. We have the dialysis, electrodialysis, gas separation, evaporation, and liquid membrane process. You see here, this is the micro filtration, or you may say it is the schematic diagram of your simple membrane process where there is a membrane is there. So at the one end we have the solution which gets filtered through this membrane to get the permeate. Then the membrane phase can either be non-porous, maybe microporous, mesoporous, or macroporous. So these are the dimensions. When the pore size is 20 angstrom to 500, it is called mesoporous. The pore size is more than 500, it is macroporous. So a uh, non-porous means no porous is there. A membrane can either be a solid or a liquid. It can be polymeric material, inorganic refractory compound, or a metal or their composites. So the performance of a membrane is defined in terms of two simple parameters, that is your transmembrane flux and solute retention or solute selectivity. So transmembrane flux or permeation rate is the volumetric or mass or molar flow rate of a fluid passing through unit area of membrane surface per unit time. So transmembrane flux of any species is directly proportional to the driving force. So how in what at what force or what pressure you have applied the sample on the membrane for separation, and accordingly your transmission flux is calculated. And if the driving force is described, it is also inversely proportional to the thickness of the membrane. If the membrane is of small thickness, then the membrane flux is higher, and if it is the thickness is more, then your transmembrane flux is lower. The value. And if the driving force is described in terms of hydrostatic pressure gradient delta P, or partial pressure difference delta Pi, or concentration difference delta Ci, then across the membrane, then Ji, it is the transmembrane flux. It is a Pi multiplied by the delta P or delta P or delta Ci divided by delta, where the ratio of permeability of species I, that is effective membrane thickness, is sometimes called permeance. And another parameter is there which is known as selectivity or retention or selectivity of the particles. A selectivity coefficient is there. So how the membrane is allowed the selective particles to pass through it. The equation is alpha AB equal to PA by PB, where your selectivity is calculated. So some important membrane processes, as we know, this may be microfiltration, ultrafiltration, nanofiltration, or reverse osmosis. So in reverse osmosis, I already discussed. It is in this process the only the solvent particles are allowed to pass through a semi-permeable membrane. The solvent particles are allowed to pass through a semi-permeable membrane from a higher concentration to lower concentration part. This is your reverse osmosis. The see here, this is the solution, this is the pure water. So the solution is having the higher concentration, that's why it is solution. So pure water contain the lower concentration of your salt. So this membrane is the semi-permeable membrane, which allows the only the solvent particle from solution, that is higher concentration, to pure water segment, that is the lower concentration part. So this is an example of the reverse osmosis, which is applied to the water purification mechanism, and all the water purifiers, whether it is aquaguard, Kent, or live pure, or anything, the same mechanism is applied. That is the movement of solvent particles from the higher concentration to low concentration, and your accordingly your separation was made. Then in nanofiltration, we have the scale of 10 to the minus 9 angstrom, and in this process, the it's slightly different from RO process in the sense that permeating species in this case is solvent as well as low molecular solute or low valency solutes. This process also operates with hydrostatic pressure difference across a semi-permeable membrane, having a pore size which is slightly larger than the RO membrane. The pore size which is 10 to 30 angstrom, and here in RO the pore size is 10 angstrom. So it is the difference. So in ultrafiltration we have the pore size of 30 to 200 angstrom, and in micro we have the pore size of 1 micrometer. Micrometer, sorry, micrometer. In dialysis, dialysis is a membrane separation technique or process in which microsolutes permeates across a membrane as a result of concentration, and we have the particular range of pore size of membrane that is 20 to 60 angstrom in dialysis. And as we know, dialysis is a medical process by which the total blood of the body is exchanged, or it may be filtered, or it is exchanged to a new blood. So there are the two veins, or we may say yes, two veins are connected to a dialysis machine by which in one pipe the blood is out and in one pipe new blood gets in. So here it is written the most common application dialysis process is the purification blood to reduce the toxic end products of metabolism in a patient whose kidneys are failed. It is the single largest application of dialysis process and is known as hemodialysis. Hemo means blood. Hematology, study of blood is hematology. So dialysis is applicable to blood purification. So it is called hemodialysis or artificial kidney. The process is discussed in detail in subsequent section. So electrodialysis. So also in this process we have some electrodes are there, cathode and anode, and the different segments or different part of the ions are separated based on their charges. So gas separation is there. In the concept of separating gas in membrane is more than 100 years old, but the widespread use of gas separation membrane has occurred only within last decade. Membrane separated gases only if some components pass through the membrane more readily as compared to other. The typical membrane process for gas separation operates with hydrostatic or partial pressure difference across the membrane. The degree to which gaseous components are separated is governed by ability of the membrane to discriminate between the two gases. So this is how the gas separation is done. We have the for evaporation in this process is membrane separation. And just see here, this is a feed mixture of A and B, and this is the membrane we have. And gradually what happened, the mixture of A and B gets separated. We have a separate quantity or separated uh, part of your NH3 to A or B. So whether this membrane is allowing A or B depends on the type of membrane as well as the type of component present in the mixture. Then liquid membrane process. So in this process we have the Two-phase barriers are there. If one component of a mixture moves through the membrane faster than the other, separation is accomplished. A membrane is basically defined on its separating performance and not necessarily it should be a solid. Liquids that are immiscible with the source and receiving phases can also be used as membrane. Different solutes will have different solubilities and diffusion coefficients in a liquid. The product of the diffusivity and solubility is known as the permeability coefficient. And this is all about liquid membrane process. So in liquid membrane process, we have the bulk liquid membrane BLM, a relatively thick layer of immiscible liquid which is used to separate uh, the source and the receiving phases. To provide thinner liquid membrane, the liquid can be impregnated in the pores of the microporous membrane. This configuration is known as an immobilized or supported liquid membrane, ILM or SLM. So the emulsion liquid membrane ELM is also known as liquid surfactant membrane. The emulsion liquid membrane is then dispersed in the feed solution and the solute transport takes place from the feed phase to the internal receiving phase. We have the transport in supported liquid membrane, co-transport and coupled transport. Here the ion gets attached to your NX minus plus with this membrane. So these are all combined to with the membrane with the CnXn, and after the we have the splitting process where the membrane gets separated and we will get the ions. Here also in the same manner we have a organic membrane, we have CH membrane, we Mn plus is there and accordingly the ion gets separated by this process, that is the H plus ion also separated from the membrane. So we have the SLM where the pH gradient is there, and here also we have the distribution coefficient, equilibrium coefficient, that the MC2 concentration plus H plus concentration square. The square is not here because it should have square divided by the Hc square concentration into M2 plus ion concentration. Then we have the feed phase, membrane phase, and receiver phase. So like this, we have the membrane which combined with this a sample of different ions to form a complex, and accordingly the membrane gets back, and the your ions gets filtered or separated. So one is sieving is there. This is simplest type of membrane. Is one that function merely as a sieve. In if such a membrane has to be effective, the solvent molecule must be much smaller than the molecules or ions of the solute, and the pore size of the membrane must be intermediate between the two. We have the solution diffusion process. We go through this. We have the preferential sorption capillary flow is there, where the capillary action is there through a very thin pipe or thin diameter. So preferential sorption capillary flow mechanism was the fundamental approach for the practical development of reverse osmosis process for the converting seawater into potable water. So thin pipes are there which uh, the capillary action is there. With the Donan effect, the ion selective membrane shows selective permeability towards ions of particular sign. Such membranes are ion exchanger in sheet form, cation exchanger being selectively permeable towards cation, and an anion exchanger exchange showing the same. Just go through this. We have the Norsen flow, and which is one of the possible mechanisms cited to explain the gas separation. In surface flow, we have the formation rate of we have the formation rate of Gaseous molecule through the membrane may be enhanced in some cases by surface diffusion mechanism. In surface diffusion, gas molecules adsorb to the surface of the pore of the membrane and then diffuse along the pore walls. Then facilitate diffusional transport. When a simple diffusion process is coupled with chemical reaction, the net permeation rate may be greatly affected. Such a diffusional permeation is called facilitated diffusional transport. In active transport, go through these things, osmotic phenomenon already discussed. This is a movement of solvent particle from lower concentration to higher concentration. So here, if the movement from solution of part A to part B, then we have the lower concentration is at part A and the higher concentration will be at part B. Then the your osmotic pressure pi, it is used to stop osmosis and check osmosis, and this is the thermodynamic derivation where the chemical potential as well as the free energy with your entropy and differential temperature, volume with differential volume, pressure is here, and as we know the chemical potential, it is the change in the keeps free energy with change in number of moles at a constant temperature, pressure, and n, and the dV by dn, it is the uh, di bar, that is the partial molar volume, and after that we have the net equation for your osmotic pressure, that is pi equal to nRT or pi equal to CRT, where is here pi equal to CRT, where C is the concentration of the solution and N is the number of moles. The reverse osmosis we have already discussed. The reverse osmosis is the movement of solvent particles from higher concentration to lower concentration. Accordingly, the equations are made. The basic equation we have the process parameter, the solution diffusion mechanism, where this is the water flux, and these are the parameters multiplied divided by RT by delta X. So concentration polarization results in from the buildup of highly concentrated solute on the membrane surface as compared to the bulk fluid solution. In the dialysis already discussed, some mathematical applications are here, that is diffusion solute flux JD, which is the multiplication of K dm delta C divided by delta X. So dm denotes the solute diffusion coefficient, delta C is the concentration gradient, and K is the partitioning coefficient. Then followed by electrodialysis, where different electrodes are applied for the dialysis process. We have the column efficiency beta will be here, and accordingly the fixed fast law was resulted, and we have the equation with some application of our membrane separation based on your microfiltration, nanofiltration, ultrafiltration with reverse osmosis. Depending upon the type of or size of the particle that can be separated from the solution. So hemodialysis, this is the purification of blood, production of table salt, protein recovery. Then you have ion selective membrane electrode is there. So on the basis of the ion, the membranes are selected. Then we have the ion electrode and the which type of the membrane may be used, what is the concentration range as well as the major interferences are what. For H plus, the glass type membrane is used, plus A plus, it is the aluminomycin membrane may be used. So specific gas probe, detection and analysis of particulate contaminations. These are all applications. Microbiological application, that is microporous membranes, are important for the detection of microorganisms in foods, beverage, pharmaceutical product, and potable water sources. So this is the overall the discussion on our membrane separation. So in the next part, we will discuss the last unit of your program, that is your electrophoresis. This is the migration of your particles from to their respective electrodes. Okay, so let's have a break of 10 minutes, sorry, 5 minutes. Then we will discuss the second part of your, or this is the last unit of your MCH-02 paper, that is electrophoresis. So for 5 minutes, let's have a break. Then we will continue. Thank you. Thank you, students. So now it is time to discuss the last unit of your MCH 02 paper, and it is all about your electrophoresis. So electrophoresis is nothing but the movement of ions or the movement of ionic particles to the respective electrodes in an applied electric field. Like we know that the cations will move towards, or the positive ions, cations will move towards the cathode having the negative charge, and the anions will move towards the anode. So let's have the PowerPoint presentation first, then we will move to the next page. And your Arnett is regarded as the father of electrophoresis, and these are some contents of this PowerPoint presentation. Then, as already pointed out, that it is the migration of charged particle to their respective electrodes under the influence of an applied electric field. That means the positive charges that are known as the cations, they are moved towards the cathode, and the negative charges as the anion will move towards the anode. And the rate of migration of an ion in an electric field depends on. So, is it visible, students? Tender and Vijayalakshmi? The PowerPoint presentation is visible. Okay. So the rate of migration depends on different factors like the net charge of the molecule, size and shape of the particle, the strength of electrical field, properties of supporting medium, temperature of operation, and ionic strength of the buffer solution. And what should we expect if the macromolecules has a net charge Q and we apply an electric field? If the macromolecule has a net charge of Q and we apply an electric field, so this will be F equal to Q into E, where your a frictional force will be there, which is BFI, and where F is 6 pi eta A, which is the uh, known as the surface energy, out of which velocity will be QE by F. So we can also define an ion's electrophoretic mobility mu is equal to P by E equal to Q by F, where electrophoretic mobility is defined as the rate of migration, that is centimeter per second, per unit field strength, that is volt per centimeter, which is equal to mu equal to Q by 6 pi Rn, where Q is the net charge of the ion, R is the ionic radius, N is the viscosity of the buffer solution. Then effect of heat, we have the peak broadening of the sample. If the temperature rises, the peak will be broadened, the resolution will be decreased, formation of temperature gradient, convection current, resulting mixing of analytes, and denaturation of enzyme and proteins will be there. Then this is how your Ohm's law or carried out for heat and resistance. As you know, V equal to IR and I equal to H equal to I square R. So V voltage is directly proportional to your current and inversely proportional to resistance, and it is a migration rate will be directly proportional to your R. So end osmosis, which is a surface of gel is negatively charged and ions are immobile. Positive buffer orient with negative surface ion. Positive buffer will be oriented with a negative surface ion. So anode or the anion, this is the anode, and here what happens, the positive ions gets oriented with the negative surface. And here in the same way, The positive ion cloud moves towards the cathode. And macromolecules for proteins that have a sufficiently strong enough charge are able to oppose the flow of positive ion cloud and move in the positive direction towards the electrode of opposite polarity. So here, if the macromolecule is there, then your negative charge will move towards the anode and positive charge will move towards the cathode. Molecule on the surface of gel that hold a weak negative charge are pushed towards the cathode despite migration direction towards the anode. So whenever the weak negative charge are pushed towards the cathode, their migration direction is towards the anode. It is already here that the negative ions are migrated towards the anode. This is the capillary wall we have, where there is a fixed layer, diffuse layer, bulk solution, diffuse layer, and fixed layer. So we have a two-side capillary wall and two-side fixed layer, two-side diffusion layer, and one bulk solution is there. So when this is applied to an electric field, then according to ions will be migrated to their respective electrodes. So as we know, the anode and cathode, the anode is always positive ion and cathode is negative. So this is the electroosmotic, electrophoretic, and this is the total, that is osmotic and phoretic. This is how the positive charge will migrate towards the cathode and negative charge migrate towards the anode. But in the total, if the positive charge will be more, then it will attract all the ions towards the cathode. So this is known as big flow. So movement of buffer into support medium during electrophoresis, heat evolved because of passage of your because of passage of your passage of current through resistive medium can cause evaporation of solvent from electrophoretic support. So this drying effect draws buffer into support, and if significant, the flow of buffer can affect protein migration. Using lead or cover during electrophoresis can prevent some of these evaporation methods that generate excessive heat utilizes a cooling system during electrophoresis. This is a conventional electrophoresis where your cathode as cathode and anode, this is highlighted by the red and black end. So red is about your electron, that is the anode, is positive charge, and the black is for your cathode. So when it is connected to your external electric field, and whenever you put the solution or sample inside the electrophoresis chamber, gradually the ions are migrated. So as we know, buffer solution is a solution which don't allow the change of pH even after addition of small amount of acid, alkali or water to it. So buffer solution resists the change of pH. So the buffer electrophoresis has to purpose has twofold purpose: carry applied electrical current. They set the pH at which electrophoresis is carried out. They determine the type of charge, extent of ionization, electrode towards which the solute will migrate. The buffer ion strength will determine the thickness of the ionic cloud. So it is that some amino acids which isoelectric bonds is there. So pre-albumin has the pH range of 4.7, albumin 4.9, and gamma globulin 7.2. And this is a pH scale we have. So this is the acidic, and this is the basic part, and the middle one is the neutral. So commonly buffer used, the hard phosphate buffer with pH around 7, the pre-sporate EBTA buffer around 8, and so on. So these are some buffer examples which are frequently used with different solutions. Then what are the supporting medium? It is a matrix in which the protein separation takes place. Various types has been used for the separation either on slab or capillary form. Then separation is based on charge and mass of protein depending on the pore size of the medium. Then we have the chemical nature and inert availability easily, electrical conductivity. We have the electrical conductivity of high, adsorptivity of low adsorptivity, desirable sealing effect, controlled porosity, high transparency, low electroendosmosis, visible visualization, low toxicity, and easy preparation. So that's why electrophoresis techniques are frequently used for your separation of ions. So these are some supporting medium, that is starch gel, cellulose acetate, agarose or polyacryl amide gel. So types of electrophoresis, we have zone electrophoresis, and under zone electrophoresis we have the paper electrophoresis, chain electrophoresis, cellulose acetate electrophoresis, isoelectric focusing, and immunoelectrophoresis. So in paper phoresis we have the paper, which is acts as the supporting medium. So gel is used, cellulose acetate paper is used, isoelectric point may be used as the reference point, and immunoelectrophoresis also is there. So moving boundary method, in this method we have the capillary electrophoresis where thin pipes may be used, and uh, iso isotachophoresis. This is a paper phoresis where paper is used and the sample is just pour is it is placed on the paper, and when the both side of the paper is heat with different electrical conduction, then accordingly the ions gets passed to that paper. So filter paper Batman 1 may be used with strip size of 3 mm or 5 centimeter long. So separation takes place in 12 to 14 hours. It is economical, easy to use, but disadvantages is the macromolecules like protein, hydrophilic molecule cannot be resolved properly due to the adsorptive and ionogenic property of paper. Then electroosmosis. So in gel electrophoresis, the supporting medium is a gel material acts as a molecular sieve, and here gel is a colloid in a solid form, that is 99% of water. It is important that the support media is electrically neutral. Different type of gel which can be used are agarose gel, starch, polyacryl amide gels, etc. We have the agarose gel. This is a linear polysaccharide, uh, and this is a repeating unit of agarose, alternating unit of galactose. So used in concentration as 1% to 2%. The gelling property are attributed to both inter and intramolecular hydrogen bonding. Then we have the pore size, that is controlled by the percentage of agarose that is used. And large size pores are formed with low concentration and vice versa. Purity of the other roads is based on the number of sulfate concentration. Lower the concentration of sulfate, higher is the purity. So this is how your agarose gel is made. So what are the advantages of this? It is easy to prepare and a small concentration of agar is required. The resolution is superior to that of the filter paper. Large quantities of protein can be separated and recovered. It absorbs protein relatively less when compared to other medium. Sharp zones are obtained due to less absorption. In the disadvantages, resolution is less compared to polyacrylamide. Different sources and batches of agar tends to give different result and purification is often necessary. And what are different applications? These are applied for the separation of macromolecules like DNA, protein, hemoglobin variants, and isoenzymes. And isoenzymes. So this is the your soul state under different temperature condition. We have the initial gel formation. So by aging, we will get the final gel-like structure. Then this is how the uh, casting a tray for making gel slab. So this is a tray. So on which the gel is now placed, and it is with the help of this uh, plate. Uh, the gel is uniformly spread over the your tray, and your with the help of micropipette the samples are placed, and after that the electrical connection was made, and by virtue of electrical conductivity or electrical migration, your ions are separated. So troubleshooting discontinuities in sample application due to dirty applicator, even uneven absorption by sample forms, then your inclusion of air bubble if sample is divided into gel. So this is known as sample comb. Okay, this one. So unequal migration rate due to dirty electrode which cause uneven application with liquid, uneven wetting of gel, uneven wetting or cutting of wicks. So this is how after your electrophoresis, this is how the migration of ions are separated, and we will get the slides like this. So this is distorted protein zone caused by bent applicators, over application, inadequate blocking of sample, excessive drying of electrophoretic support, incorporation of air bubble during sample of applications. Unusual band. Unusual band may be obtained by hemolyzed samples at frequent causes of increased beta globulin. A band occurring at starting point of electrophoregram may be fibrinogen. A typical band is there. It is an irregular but sharp protein zone is seen at starting point. Actually, denatured protein resulting from deteriorating serum. So the sampling, it is too much sampling, blot excess sample is there, and if it is low sample, then band resolution will be lower. So the sampling must be of appropriate dimension. So run taking long time. So due to too much current passes and that leads to drying of gel, decrease current to 25 to 50%. So this is how your gel is spread and migration of ions will be there. This is blue and this will be in color, that is one anode and one is cathode. Just see here, this is a beautiful separation of ions, that is DNA sample is there, and your uh, that is your known as DNA test by your gel electrophoresis. So this is the albumin, and we have the migration of components with different electromigration characteristics. And this is already discussed. Then we have the polyacrylamide gel electrophoresis, where the your thiosulfate is now two ions of the sulfate free radical, and this free radical is reacted with the acrylamide monomer, and accordingly the chain will be over. Then the next one is your sodium potassium sulfate, that is STS, polyacrylamide gel electrophoresis. Polyacrylamide gel electrophoresis. This is STS phase. That is sodium potassium sulfate polyacrylamide gel electrophoresis. It is most widely used method for analyzing protein mixture qualitatively, useful for monitoring protein purification as separation of protein is based on the size of the particle, can also be used for determining the relative molecular mass of the protein. It is an anionic detergent, HDS. The sample is first boiled for 5 minutes in buffer coating. Beta mercaptoethanol or STS may be used. Then we have the on average one, this is STS molecule bind for every 2 amino acid residue. Hence, original negative charge is completely swamped by the negative charge of STS molecule. So this is just a amino acid residue of the histidine, we will say. So this is when paired with your STS, then the amino acid chain gets completely swamped by the negative charge of STS. This is the component with the negative electrode. We have the different segments, and this is the protein we have, and in the down it is the positive part, and it is deep in the buffer solution. Then in STS stage, the components of the amino acid or big size protein get separated. This is a demonstration of that STS page chromatography, sorry, electrophoresis, and this is how your separation is done. You see here, separating gel is here. You have a tank of cathode and anode at the bottom, and buffer solution tank, and when the power supply is on, your sequence now move to the respective electrodes accordingly. Then your stacking gel. So ordering or arranging ordering or arranging and concentration the macromolecule before entering the field of separation 4% of acrylamide. The purpose is to concentrate protein sample in sharp band before it enters main separating gel. Running gel, the actual zone of separation of the particle molecule based on the mobility. So this is how your gel electrophoresis is going on. Then we have the movement of particles. Then the application came, that is the research tool measuring molecular weight. peptide mapping, protein identification. Then we have the determination of your sample purity. In separation of protein and establishing sites, blotting smaller fragments of DNA. What is the advantages? Gels are stable over wide range of pH and temperature. Then gels of different pore sizes can be formed. Exhibit reasonable mechanical strength, low endoosmosis effect. Gel preparation and casting is time consuming. This is carcinogenic and complete reproducibility of gel preparation not possible. You have the staining, that is fluorescent stains, that is ethidium bromide for nucleic acids, silver stain for protein gel, dye-based, that is cosmic blue for protein band, and tracking dye, that is your xylene cyanide. So these are all the staining, that is coloring material. So buffer gel, we have the, it is done by using the polyacrylamide gel of 7.5%. We where STS absent, pH up to 8.7, proteins are separated according to the electrophoretic mobility and seeding effect of the gel. Then it is the isoelectric focusing field described by Sweden and Vinson. This method is ideal for the separation of amphoteric substances. Method has high resolution. It is able to separate the protein which differ in isoelectric point by the little as little or change of pH of 0.01. So this is how your isoelectric focusing is made with different just minute change in pH. Then establishing pH gradient, we have the amphiphites, that is neither basic nor acidic, must detect pH codes, should have conductance at their pH, then low molecular weight, solubility in water, low light absorbance at 280 nanometer, available commercially with pH band of 311. Example are ampholine, Parmalite, and Biolites. It is about separation of proteins by isoelectric focusing, where the proteins get separated using the same principle of your electrophoresis. And these are some applications that are highly sensitive for studying the microheterogeneity of proteins, useful for separating the isoenzymes, teaching research in enzymology and immunology, then forensic food and agricultural industries have application for this focusing, this electrophoretic focusing. In two-dimensional polyacrylamide gel electrophoresis, the principle is STS-H or our technique combined with IEF as first dimension which separate according to the charge. And these are the some points of our two-dimensional polyacrylamide gel electrophoresis, that it is a combination gives sophisticated analytical method for analyzing the protein mixture. Its size vary from 20 in nanometer to 20 centimeter or 20 into 20 centimeter to the mini size that is IEF is carried on acrylamide gel of 18 into 3 centimeter square with 8 meter area. So it is area. After separation, it is placed on 10% of HDS cage for further separation. Used in field of proteomics can separate 1000 to 2000 protein from the cell or tissue extract. So this is how your two-dimensional electrophoresis is made, where the PSN is from 4.0 to 10.0 and the protein gets separated. Then isotachophoresis. This is used for separation of smaller ionic substances. They migrate adjacent in contact with one another but not overlapping. The sample is not mixed. The sample is not mixed with the buffer prior to run. Then current flow is carried entirely by the sample ions. Faster moving ion migrate first and the adjacent ones next with no gap between the zones. Then we have the all ions migrate at the rate of fastest ion zones. Then it is measured by UV absorption. Then what are the applications? Separation of small anion and cation. Amino acid can be separated. Peptides, nucleotides, nucleosides, and proteins. All these can be separated by this two-dimensional electrophoresis. In pulse field electrophoresis, the power is supplied or applied alternatively to different pair of electrodes. The electrophoretic field is cycled at 105 to 180 degree, because of which the molecule have to orient to the new field direction. This permits separation of large molecule like DNA applied for typing various strain of DNA. So this is the base where the immunoelectrophoresis. Immunoelectrophoresis refers to precipitation agar under an electric field. It is a process of combination of immunodiffusion and electrophoresis. An antigen mixture is first separated into the component parts by electrophoresis and then tested by double immunodiffusion. So antigens are placed into wells cut in a gel without antibody and electrophores. A trough is then cut into the gel into which antibodies are placed. The antibodies diffuse laterally to meet the diffusing antigen and the lattice formation. So these are all your biological related phoresis mechanism. So this is the principle involved. Apply to slide layered with gel. Antigen mixture placed in well is separated into the individual antigen component according to the charge and size. Then we have the separation process is like this. I will share this PDF with in your WhatsApp group. So do not worry. We have the antigen separation like this in electrophoresis, where the antibody antigen soluble is there, zone of equivalence, that is visible part is there. So all these are very important or microbiology or biological experiments that are made for separation of antigen and antibodies. Electrophoresis of sample, that is your antiserum drop samples where diffusion of antigen and antibodies precipitate transformation is all sample. So agarose gel is prepared on a glass slide. This is the procedure how your separation was made for your blood sample. Then the result that the presence of electrical precipitin acts represent antigen antibody interaction. Absence of formation precipitate suggests no reaction. Different antigens can be identified based on intensity, safe position, etc. This is the application we have. The test helps in identification and approximate quantization of various antigen in immunology. Suspected monoclinical and polyclonal gamma patches used to analyze complex protein mixtures containing different antigens. The medical diagnostic uses of value where certain proteins are suspected for being absent. This method is useful to monitor antigen and antibody activity. So this is the capillary electrophoresis we have, where different dimension of the capillary tube or narrowed to four capillaries are there, where the length to silica capillary tube, polyimide packed with buffer is used, and this is the component of your capillary electrophoresis apparatus, where the reservoir is there, then it is capillary inlet, electrolyte buffer, then it is a power source, then it's a capillary tube we have, then the detector computer is here, and the sample applicator, this is the sample applicator we have. Then sample application is done either by one of the method, high voltage injection or pressure injection. So for buffer reservoir, is replaced by the sample reservoir, high voltage is applied, buffer reservoir is placed again, and voltage applied for the separation. Anodic end of the capillary is removed from the buffer and placed in the air-fed sample. And this is a voltage applied, that is up to 50 kilovolt. The component migrate at different rates. The same principle, electrophoresis is here, positively charged molecule is the cathode, and vice versa. And this is the detection of your UV absorbance versus time using capillary electrophoresis. These are the troubleshooting. Absorption of protein to the wall of the capillary leads to smearing of protein, viewed as peak broadening or complete loss of protein. Use of neutral protein group to the inner surface of the capillary. So clinical application, multiple myeloma testing. This is hemoglobinopathy. Then we have the advantage over conventional method. It is online detection, improved quantification, almost complete automation, reduced analysis time. Then microchip electrophoresis. It is current advanced method. Development in technique include integrated microchip design, advanced detection system, new application, protein and DNA separation can be done. This is the instrument we have. That is your electrophoresis separation, how your microchip is used for the separation of ions to their respective electrodes. The detector, laser influence fluorescence, electrochemical detector, pulse amperometric detector, and sinusoidal voltmeter. Then this is the references for this presentation, that is clinical chemistry and YouTube and this are there. So thank you. So this is all about your electrophoresis, in which we have already uh, discussed all these electrophoresis technique for the separation of ions, and so now the platform is open. Anyone having any question or related to today's class or previous classes or anything related to your program, you may ask or share your experience, and after that we will wind up the session.
सर इसका पेपर पैटर्न बता दोगे एक बार?
क्या बोले?
पेपर कैसे क्या अटेंड करना वो बताओगे एक बार?
अब पीजीडीएससी का जो भी आपका जो एग्जाम होता है वो शायद 10 मार्क्स का क्वेश्चन आता है, जस्ट वेट में देख लेता हूँ। पीजीडीएससी क्वेश्चन आपका जो एग्जाम में आता है वो शायद अवेलेबल होगा। आपको ये जो क्वेश्चन आएगा, आई थिंक इट इज 10 marks question of 15 marks in total, I think, and you have just wait. एंड ये जितेंद्र, आपने कुछ भी एग्जाम अभी तक अटेंड नहीं किया ना? तो दिस इज योर फर्स्ट सेमेस्टर, आई थिंक।
इस
Okay, okay. Just wait, just wait. The questions are generally available in the website. You just go through this PGDSC with the question paper of June. So in the, I just sharing this link with you in your WhatsApp group. Just wait. I'm searching. PGDSC. Yes, this one. PGDSC. So the question is not available here. That is one. You have physics, mathematics, biology, MCH. Yes, this one. Yes, this is my part. Yes, this is the question. You see, is it visible, Jitendra?
यस सर विजिबल.
Okay. So in this way, you can download the different questions. Just see here, you have the 75 total mark, 3 hours of examination, and you are advised to attend 5 questions. That means one question carry 15 marks of different subjects are there. Like in your first question number 1, we have 3 to 5. Like your name, all the criteria for selection of separation method, draw the nature of plot between pH and your distribution coefficient, write the criteria for the selection of stationary phase, adsorbate, then the ion exchanger, ion exchange. Just see the question. The questions are like this: define chromatography, who discovered, then the familiar equations are here, then concept, details, easier in the chromatography, and we have the resolution, number of plates. So like this, your question will come 15 into 5. Then just go to the website and download all the questions of this year, and accordingly you just attend the questions, and just try to remember the key points and your equations for your examination. Okay.
Okay, sir.
Okay. So regarding your practical, you will get email confirmation to your registered email ID, and you just submit your assignment within the due date. And regarding your theory paper, you just go to the online material which is available in the website, and in the month of December you have the theory examination, and I think your assignment date is just check the website. Okay, everything is there. And if Vijay Lakshmi, any question? Okay, so this is the first time that the attendance is very poor for PGDSC program. Generally, 10 to 12 or 15 students are attended the class. So it's okay that IGNO is conducting different courses and online classes, but students are not that much of serious to attend the classes. Classes. So, so lastly, I thank you both of you, especially Jitendra and Vijay, to stay with me for the last 6 classes or last 8 to 10 days, and we discuss various aspects of separation techniques, starting from physical separation to electrophoresis, and between this we have discussed the solvent extraction followed by different chromatographic techniques, and ion exchange, side exclusion, and your electrophoresis. And today we have the first part, that is your membrane separation also. So uh, so just go through this material very carefully, and I will share all the. I already shared the two PPTs, and today I will share the next PPTs in your WhatsApp group, and hopefully this will help you in future. So thank you to all, and hopefully we will meet again in different courses and different platforms. So lastly, so thank you on behalf of Regional Center for English. I thank you all for the patience hearing and active participation. And so thank you. The class is officially over, and tomorrow you will have the class, that is online class. Tomorrow you have the class, that is your class of Dr. Jyoti Prakash Dhar, who will be teach you MCH-03 paper, that is a spectroscopic method. And under this you have the electromagnetic radiation followed by ultraviolet UV spectroscopy. Then you have the infrared spectroscopy, the UV, infrared, then NMR, mass, all these spectro infrared is infrared. The third unit will be Raman spectroscopy, and followed by different spectroscopy techniques are here. These are very frequently used in different uh, analysis of samples in industries, in chemistry labs, in research. All these things are very useful for characterization of your sample, colorimetry and phosphorimetry, followed by your application of this one. Then we have the block 3, that is NMR, flame photometry and its application, atomic fluorescence spectrometry, and NMR should be there. That is one of the most important atomic absorption, atomic emission, application of both these spectrometers. The last part we have the, and the last block you have the NMR. Okay, so hopefully you have a good experience in these last 6 classes, and thank you to all for your patience saving. Now the class is officially over. Thank you.
Thank you, sir.